Today we're going to be discussing a topic that has accompanied us. It's an unusual image. It's accompanied us through a number of different lectures. When we covered option and try, and the book covered either as well. When we've covered streams, when we've covered other collections in Scala. I've made note of the fact that what we're actually dealing with in those cases are examples of a more general category of things called monads. Okay, and monads are an important concept in functional programming. They're an important concept in Scala, and they play important roles in Scala with Spark. So it bears some understanding about how they function, why we use them, and how they provide a functional alternative, in my view, and one that's recommended quite a lot compared with traditional mechanisms that you'll see, say, in object-oriented programming for extending a language, for achieving generality that you'll otherwise see in things like aspect-oriented programming. So today's class, and maybe next time as well, we're going to be going a little bit lighter on the practical exercises. We'll have some of those, but it'll be somewhat lighter. And we're going to be emphasizing certain concepts. And those concepts are related directly to the concrete example covered in this chapter, which follows it through to the end on sort of keeping state in a functional fashion, where particularly the example uses random number generation to illustrate monads. But as with many examples in this book, Functional Programming in Scala, that example brings out the concepts in a concrete way, but it tends to be fairly abstract and demanding at a conceptual level for how it presents things. It may not be clear how it generalizes. In addition, it doesn't really make central use of Scala's mechanisms for built-in mechanisms for doing monadic operations, which make use of flat map, filter, etc., in a way that's captured by particular classes. So what I'm going to do is I'm going to switch over now, not to hands-on exercises so much as to a set of slides. And these slides, I'm hoping, will unpack some of the concepts that you've seen illustrated in the book, and help you start to work towards understanding of monads. Monads are a notoriously slippery concept. By slippery, I don't mean that they don't have clear definition. They do. And in fact, the book in its later portions introduces the monadic axioms, which are specific criteria, a small set of kind of specific criteria that are required to be a monad, and discusses the implications of that. Within today's lecture, what I'm going to be instead hitting on is sort of a more visceral introduction to monads. Now, we're having a bit of an issue with the resolution here, so I hope you'll forgive me if I just go and adjust this resolution slightly so that we have a common mirrored resolution. Okay, here we go. What I don't know is how Google Hangouts will handle that. Can you see my screen still on Google Hangouts? Okay. Okay. Is that Google Hangouts? Yeah.
No, that's what you do.
Sorry. So sorry, I meant YouTube.
Oh yeah, that's good.
Sorry, YouTube uses Google Hangouts for messaging, and so I hashed it to the same bucket. Sorry. Okay. Thanks. So within this set of slides, I'm going to be trying to provide some motivation for monads, and I'm going to be providing an introduction to some basic properties of monads, not in an axiomatic way, not in a way that builds up from first principles, but in a way that points to common features. I'm going to be giving some examples of monads, and I'm going to be showing why we do certain things with monads the way it's illustrated in the book. And as time allows, we may further go into some aspects of how Scala in particular facilitates monadic operations. Quite possibly a fair bit of this will be left till next time. Okay. Okay, so we've been talking in this class and some in the book about pipe and filter patterns, but these pipelines that we build up. And in fact, they play a central role in Spark in general, and Spark's machine learning library, SmartML in particular, being reified in pipelines there that are explicitly recognized as pipelines. There's no mystery as to why that is, because pipe and filter patterns are really powerful ways of characterizing computation, in a way that's simultaneously transparent, fairly concise, fairly modifiable, and fairly modular. You may remember that we had a pipeline, for example, that counted the number of occurrences of particular words within a document. And by just changing one or two items in it, we could get it to instead count the number of occurrences of words of different lengths, right? And similarly, if we had changed just one or two other aspects of it, we could have had the original pipeline using, data gathered from a web page and the text from that web page, et cetera. So the point is that these pipe and filter patterns provide us a way of kind of characterizing computation that's flexible, powerful, quite general, and that's transparent, that allows us to sort of reason through it, which is very important in software engineering. So we have, successive operations. This is actually, does anyone recognize what language this is? I'll give you a hint. It's not Scala. It's Java 8. Yeah, this is Java 8. And this gives an example of pipe and filter in Java 8, which differs a little bit from Scala. In many ways, it was inspired by Scala, but some of the extensions there. But here you can see we have a filter, we have a group by, we have collections that count the number of people of a given age, etc. Okay, this is counting the number of infectious people who are of a certain age, I think. So there's this kind of a flow of the pipeline from start to finish, and you have some additional texture associated with this counting. Now, a challenge that we discussed previously is that we've been dealing for simplicity with mostly linear pipelines. Sometimes we have nonlinear flow of control. I'm not just talking about looping over the contents of, a file. I'm talking about situations where, in particular, we might have handling of special cases like nulls, exceptions, cases where there just doesn't happen to be a value that falls in a certain range that we're seeking, or where we're dealing with asynchronous operations, like going out and fetching a web page. And we don't want to just be sitting and blocking, waiting for that web page to respond, to that web server to respond. Or maybe we're going out and gathering information from a service online, or from a long latency device like a tape drive or something. And there's an operation we want to start, And we don't want to just block this thread waiting till it responds. These are operations that might be more naturally handled in an asynchronous way, meaning we'd like to do something when it comes back to us, or time out if it doesn't come back to us in a certain time. So how do we handle these elements? Well, we've been seeing components of that, right? We've been seeing, for example, handling exceptions. What do we use to handle exceptions? We used a special type called, begins with T, try. Good. Okay. Great. No need for hangman with that one. Okay. And to handle cases where sometimes data is missing or it's present, we used what in Scala? Option. Right. And, you know, you could have either to represent you either of this or that, for example, more generally. And it turns out there are these really nifty things called futures, which we'll probably introduce, that support asynchronous operations. And they're basically promises of future values. They might hold the current value, but they promise you that at some point there'll be a value here. And they let a function that you pass as a higher order, as part of a higher order function, you pass along a function that can be called when it returns. Now, all of these and many more are examples. They all share certain characteristics. It may not be obvious. Perhaps the most obvious characteristic is that they're novel to you. But in fact, they're all what are called elements of monadic types or monads. Okay. We use the term monad for short here. They all share certain characteristics of how they process things. So what are these monads? How do they function? What role do they play? Other than being kind of nifty little hacks, what unites them? Well, a monad is a type that allows, characterizes the type that allows the software developer to sort of customize the meaning of what it means to chain together a sequence of steps. And the terminology that's introduced in the book, which I rather like, and it doesn't originate in the book, but it's echoed in the book at one point, is it analogizes them to programmable semicolons. All of you are familiar with, in many languages, including Java, other languages in the C family, you have semicolons to finish statements, right? The idea here with the notion of programmable semicolon starts to get at the notion that this sequencing from step to step, from one statement to another, rather than just always proceeding in the same defined way, maybe sometimes we want to trace information about what's going on. Maybe we want to log things, for example. We want to do logging along the way, that I've reached this point, that I've reached that point, that I've reached that point. Or maybe along the way, I want to bring along some sort of debugging information on where values came from, where they were first computed. Or maybe I want to bring along provenance information. This value that I'm using here, what data sources did it originally depend on? Maybe it came from a combination of values from 3 different data sources. Maybe I want to know that. Or maybe I want to know the units, meters, you know, years, volume associated with a given quantity. I want to carry that along with the quantity. In addition to the value, I want to know, is this a value describing things in square meters or square feet or what have you? Maybe I want to carry around its dimension, or I want to carry around its unit. And if you could imagine those semicolons playing a role to kind of bring along extra information beyond just sequencing, this statement goes after that one, you're starting to probe this notion of monads. It's kind of like you can take a program and layer on it extra types of information. And the recognition here is that there's an opportunity for separation of concerns here. If we use these monads in the right way, we can kind of have a separation of concerns with our program. We can use monads to capture certain information, layer it in to this program in a modular way, without having to hard code the fact that we're logging at certain parts of the program. We could just add it on in a modular way or remove it when we don't need it, for example. Okay. Now, high level, but it gives some intuition for what's being talked about here, hopefully. Now, monads can be thought of crudely as kind of packaged values, values that are put into a package. They're kind of wrapped up with extra information. Okay, and this package into which these values are stored can store extra information. Maybe it stores the unit of the value that's within it. Maybe it stores where that value, from which data sources that value was derived. Maybe it stores information associated with where that value was first computed in the program, what line number, here. It's from zap.java line 231. Maybe it stores information about whether the value is yet computed. Maybe it's just this is a promise, and I want to know, is this value ready yet, or is it still to be computed? So the package here might not just store the value, but information about whether it's computed yet, right? And maybe when it started computing, so we can determine a timeout. Alternatively, maybe the package just stores information, either the value or it knows whether it's empty or not. All these are examples of monads, and I hope you can start to get a sense that you can fruitfully think about them, whether it's try or option or future holding a value, whether it's stream or something like that. You could think about there as being a value within the package, one or more values within the package, and then the package stores some extra information. For example, what does stream store? When I say, okay, there's values within the box, what does stream have to store? So if I'm using a stream of primes or something, what else does it store other than the values it's already computed? What does it need to store, a stream?
How it computes the next one.
Yeah, how it computes the next one. It's got to know how to give me more when I need them, right? How to compute more of them. That's what I argued was one of the powerful sort of components of the stream abstraction is it only allows us to sort of specify an infinite computation and separate it from how far we want to compute it. But it wraps up within itself a knowledge of how to compute more. So we don't have to drag around that information. Oh, this is a stream of primes. This is a stream of fibs or whatever. It just remembers what its job is in life. And you can have code that has some stream given to it. It could result from a differential equation model. It could result from an agent-based model that it's giving us successive computations, the agent-based model. Maybe the stream is reading things off of a weather report out there on the web, or it's getting data from Ethica via phones or what have you. Who knows where it's coming from? We don't have to care. And that's a separation of concerns. The stream knows how to take care of itself. It knows how to do its work. So streams have to not only store values, they have to store some information about how to get more of them. And similarly, option, has to store not only the value, but whether or not it's empty, right? There ain't no value if it's empty. If it's not empty, there's values there. So I hope you could see these are all kind of, you could think of it as like a package holding a value. Yes, you've got a value in there very often, but or more than one value, like for a stream or a collection. But then you've also got some metadata about that value, or paradata, sometimes people talk about, which is a somewhat similar concept. But it's data about what we have at some level. Does that make sense? Okay. So there's many monads, and these are a few when I've mentioned these, but there are others. Now, Java 8, I'm not going to be focusing on Java 8. I actually have a parallel version of these slides for Java 8, or for most of the slides for Java 8. If anyone's interested, I could share them. But there we have streams. We have optionals, which are comparable to option. We have computable futures, similar to future. And there's various third-party ones that provide information. Okay, so what do these monads do? What do they allow us to do at a common level? By the way, can you see if my audio is coming through there? Just to make. Okay. Don't listen to him. Listen to me. Okay. So, ladies and gentlemen, common uses of monads include, extending from my comments, maintaining metadata concerning. This says the value, the values, right? Think about stream. Think about various Scala collections, right? Array or vector, etc. Another common use is they can keep track and handle exceptional values, right? Empties, nulls, things that would lead to an error, an exception. They maintain contextual information throughout a series of operations, where values were computed in the program, from whence they were computed in terms of external data sources. And they can perform extra operations associated with this during the execution of code, like logging or tracing of a program, for example. Okay, so you might have a monad associated with logging to a file, another monad associated with logging to a website by posting, another one associated with logging to a console, printing things out. Okay, so what are some advantages here? Well, they allow for very sort of straightforward composition of functions and maintaining information values. So they allow our computation to take place while maintaining additional information and to handle alternative execution flow in a way. They can handle alternative paths of flow, such as when we have an error condition or an empty value or what have you, in a way that is just part of our pipeline. We don't have to have a separate set of branches. Every time there's an exception, we have to kind of go branch off and handle it and somehow come back. It's all part of the same pipeline. And they can really simplify and clean up code. It also provides a clean functional route to capture things like exception handling, callbacks, yes, but also inversion of control. And I would actually also put here aspect-oriented programming, okay? Which I'm not sure anyone here has directly experienced, but is a very neat technique that can be used with many languages, including Java and JVM languages. So inversion of control, is that a concept some people have encountered here? Yeah. So one common mechanism for it is dependency injection, but separation of, inversion of control allows us to have more loosely coupled objects, so that objects don't hard code what they're calling, but rather, for example, it can be specified via configuration file. And at runtime, for a particular situation, I might change that configuration file, which allows the system to be composed of different objects, but still work just fine. And with inversion of control, there's a notion of a Hollywood principle. Don't call me, I'll call you. Okay. And in fact, those familiar with any logic will recognize that in any logic, there's kind of an inversion of control. You set up a person agent, and the person agent has event handlers for when this transition is crossed, it'll invoke that event, or it'll have an event that goes off once a day to report some value out to the console, or report some value to a CSV file or whatever. Or there'll be a message handler, right? When I get a message, these things happen. Maybe it's just that I go to a certain state, or maybe I print out some information, or log it, or whatever. So that's an example of inversion of control, in the sense that it's not like I write code that says, make this agent do this, next, check this, if so, have them do that, or what have you, which is a more traditional way, top-down, of describing a program. Rather, the framework, here, the AnyLogic framework, calls off to our code at the appropriate times, right? So it schedules when this event is going to fire once a day. It handles when one agent sends another agent a message, and it takes care of invoking our code, right? In AnyLogic, do you recognize what I'm talking about? Yeah. Now, maybe too much. The issue here is that that provides great flexibility, and it reflects a more general trend towards this kind of framework calls and coordinates the action of its different subcomponents that you'll see in today's world, whether it's event handling messages, reactive programming, frameworks that we use for different types of programming. This sort of event-driven framework is very common. And at the same time, I will tell you, for non-computer scientists, it is often for those who are from, say, engineering background, not for computer science, often they find it very, very unsettling because they're used to writing things from top down. And this idea that, like, don't call us, we'll call you, it's like, where's the program? Where's the top-down program that I'm looking for? And so it's one of the reasons AnyLogic finds challenges getting certain of those from engineering background to kind of adopt it, is because they want to see a top-down structure, and it's not there. Anyway, so these are all cases where monads could be useful, can be really useful. They allow us to customize our program in a more flexible, transparent fashion. Okay, so let's talk about some defining characteristics of these monads. What unites them? Gosh, I feel we're not. I'm not fully engaging those in the room, though. I'm afraid soon snores will begin, and I won't be living up to the moment in terms of capturing things. So what I'm going to do, I'm going to go. There it is, Scala. Okay. I'm going to to make this a little bit concrete, I'm going to do some things in Scala that will mirror some of the concepts I'm talking about, just to make it concrete, right? And to get your fingers going and to lower the probability of heavy snoring. Okay, so you remember options, right? Remember options? Yeah. Okay. So with an option, we could say val a val O, and we could say it's an option event, right? Remember that? Suppose I wanted to create an option of that holds a value 3. How would I do that? Some 3, right? Yeah. Now, of course, I've been overly pedantic about this. I actually don't know. I don't need to have this option declaration because it will actually do type inference, right? So I could have just said that. But the point is, I want to emphasize that this is an option event. You'll notice, interestingly, and this relates to some examples in the book, that this one actually, it refers as a sum event, but that's actually a subtype of option event. So I wanted to bring out, this is an option, right? Okay, so this is something where we give a value and we bring it into a monadic context, okay? Option being a monad. We have a concrete value and we bring it to be a monadic value, right? By saying some of this, right? Alternatively, we could create an empty value, right? Where it's none. And I believe we could have said, O2 here is none, right? It would allow us then to to sort of have this value which is empty, right? It has the potential to hold an int. It's kind of maybe of int in Haskell language, but in this case there ain't nothing there. Okay. So here are some monadic values. Now we're going to be manipulating them in just a second, but I want to bring things on. So suppose we have a monad. Option of int was the monad there, right? It includes a value of a certain type. What is that type A for option of int? A is what? Yeah, it's an integer, right? So, for example, it's an option of int encodes the value 3, right? Now, with a monad, we have two operations that are key. One of them we just illustrated, and that's one that's variously called pure, unit, or return. Now, I'm frankly not quite sure if which is more confusing, but fundamentally what they describe in terms of names, I can imagine people getting confused about each of those because they're fairly overloaded as names. But the key thing is that this function takes in something, it returns something. What does it take in? Yeah, here it takes in an int. It takes in the type of the thing inside the monad, the values or value of values inside the monad. In this case, it's int, right? And what does this return? Begins with an M. It ends with a D. It returns a monad. That's right. It returns a monad of this. So it would be like it takes in an int and it returns a, for example, option of it, right? It's a monad. So we talk about this injects a normal value A into the monadic value. And we just did that. We did sum of A, right? We did sum of 3. And it created a monad, right? Monadic, an instance of a monad, of an option event monad, right? So we had a value 3, and by applying this function to it, it brought it into the monadic domain. Now it's a option int with holding the value sum of 3. Do you see that? So sum in Scala, sum for options, for options specifically, sum is unit, return, or pure. You could call it any of those names. The sum function performs that job here. Okay. Now, what would it be if we were if we said this is e.g. For option of A, then we have this. Suppose we were dealing with a monadic value with try. How do we do it for try? How do we bring what's the sort of equivalent for try here? How do we do it with try? Anyone?
Just try 3.
Yeah, try of 3. Oh yeah, I have to import Scala dot tilde dot. So yeah, there we go. Okay, happy. Okay, so and in general with Scala, the type constructors typically, actually, it's the companion object, companion object function. So there's a companion object for the try class. Remember, companion objects are these kind of support singletons that support values for that. And there's one called try, and it will allow us to take this and it will inject it into the monadic domain. So we get a try event, right? How about for stream? Yeah, we just say what stream 1, 2, 3, right? And this will take that and create a stream, right? So in general with Scala, we have these things that happen to be implemented through companion classes that basically create instances of it. Those are examples of pure unit or return. They're a function that takes an element of the type that's contained in the monad, here int, and it puts it into the monadic domain. Do you see that? Okay, now the other thing that we have to depend on, though, is something called bind. Okay. Now, bind conceptually, it takes two things, and it returns another thing. As we'll see, because Scala is an object functional language, it combines both mechanisms. We'll refine this notion a bit, but conceptually, it takes two things here. What's the first of those? What is this? It's a monad. Good. And what's the second one? A function mapping the type of thing that's in that monad that we gave us to another monad, possibly of a different type, B. So we might have B being the same as A, but it might be different. Might be different. So maybe we have a monad that has an int in it, and we give it a function that turns, and this thing bind, we pass it that monad, say, option of int, and we give it a function that maps from what? From integer to, say, option of double. Like maybe it takes the square root of it. And then bind returns. What would it return in that case? It returns a, yeah, of this new monad. And for the example I just gave, where we have an option of int, and then we pass it a function that goes from ints to option of double, what would this bind return? Yeah, option of double. Option of, it's a monad. Yeah. Okay, now this may seem an arbitrary thing, but it turns out it's extremely powerful. And what this bind does, and again, I'll come back to how it's defined in a sort of object functional context, it allows us to compose functions, okay, by taking a monad rep value and a function to which to apply to that, and to then compose them and return a monadic value, okay? Return this monadic value. So it allows us to kind of take what was already in here and combine it with this function to return a new value. For example, just to sort of help you understand this, maybe this is sum of 3. Maybe this is a square root operation, which returns option of 3, or option of double. And here we take the square root of 3, and it returns sum of the square root of 3. Do you see that? That could be one thing. Or, and this gets a little bit more textured, or maybe what we have in our original option value is not sum of 3. Maybe it's empty. Maybe it's none. We don't have a value, in which case we provide this function to take square roots of ints and turn them into doubles. And what does it return? Well, okay, but if this is none, what is it going to return? What's the concrete value? It's going to return none, right? So bind does more than dumbly apply this function to the contents of that. It actually considers what this monad is, and in some sense composes them. Okay, in some sense composes them. This original value, this monad, is something which could be empty. It could be a failed value, right? It's a failed computation. It could be a stream, and it has to create a new stream, etc. Now, what function in Scala? Well, okay. So I will say this. Now, Scala is not merely a functional language, it's an object functional language. And it turns out those two go together very nicely. It's not that they're in tension always. Actually, there's some things that you can do with sort of functional reasoning that are especially sweet to characterize if you have an object hierarchy or a type hierarchy. One thing is a subtype of another, okay? So they actually go together really well. But in Scala, I will tell you that bind, the equivalent of bind, which we'll get to in just a moment, is not implemented by explicitly taking a monad as its first argument. Instead, it's a method that's invoked on a monad. That sounds fancy. What do I mean by invoking it on a monad? I mean, we call a method on the monad. We don't have to pass the monad, this first monad here, as an argument, because we say to this monad, m of a, we say, do this. Here's your function. And it applies it to itself and gives us back a monad. Does that make sense? And in particular, what's that function for bind called? It's called flat map. This is flat map. Do you recognize it? You know, I recognize it's subtle, and maybe I should bring a set of binoculars. But you could see it with perhaps greater clarity. But the idea is with flat map, what does flat map get applied to? Well, it gets applied to monads, okay? Its job in life is to serve monads. And what does it take as its argument? What does flat map take? Well, let me ask this first. What does map take of its argument? If we were talking about map, put flat map aside for a second. Flat map is actually more interesting than map for reasons that are alluded to in the book. But what does map take as an argument? So if I have a vector, or I have an array, or I have a stream, or in fact I have an option, and I call map on it. Suppose it's a stream of type T, or a vector of type T, or an option of type T. What is the function that I give to it when I specify map? What does it take? What does that function that I give to map take as an argument? What does it return? Yeah, it maps concrete values of that thing to something else. So let's imagine a vector. Here, let's not imagine it. Let's do it. Are we okay with that? Okay, hearing no objections, I'm going to engage in typing activity. Okay, so here we go. Ready? Here we go. Vector of 1, 2, 3. Okay, I don't want to bore you. Okay, 1, 2, 4. Okay, dot map. Oop, dot map. And what do we have to give this? Yeah, we give it a function, right? So maybe we give it a function that, and forgive me, I'm just going to be very explicit about it this time. I'm going to take in an x, and I'm going to multiply the x times 2. Okay? And get out that. This is a function that takes in the concrete values of this, right? Which happen to be what here? Ints, right? And it returns, does this return a monad? No. What does it return? Yeah, it returns concrete things. Now, what would happen if I did this? Oh, it's subversive. What would happen if I did that? What would it return?
Vector of doubles.
Yeah, a vector of doubles. So it's not that this function can only take an int and has to return ints. Far from it. It could take an int and return things of different types, right? Okay. So that's well and good. So if we did import Scala.math. Is it capital math? Mumble. Okay, so if I were to do this, right, we get a double as well, right? True or not? True. Okay, indeed. Well spoken, man. Okay, so this is map, right? This takes in concrete contents of this, and it gives out concrete contents, right? Now, what would happen? What would happen if we did something like this? What would happen if we did vector of x? How if we? Yeah, okay, vector of x and the square root of x or something. Well, okay, sorry. I'm going to change this because it's not going to be as odd. Okay, so now suppose I do, so this is one monad and I'm mapping it, right? This takes in particular concrete things in it. It returns concrete things, the contents of the thing to return, right? Okay, now watch this. If I did sum of 3 and I do map here, and I do map of this to say x times 2, I'm just mirroring what I did up there. What do I get back?
Sum 6. Yeah,
it's an option that it's an option monad that contains 6, right? It contains ints, true or not. It speaks to us right there. Okay, now watch this. Suppose I said this. What would happen? Or suppose I said, let's not bore you all. Suppose I were to say this.
Option.
Yeah, it's going to return an option of double, right? Okay. This is map. So we're saying, hey, give me your value that's inside of you. And then the same thing was true for vector, right? We said basically, give us the value that's inside of you, and I'll give you back a value you put inside one of your same type. So vector, right? In came a vector, and out went a vector. And this returned the elements successively, just like that, right? Yeah. That's in this vector that came out. Do you see that? Okay, now watch this. Same thing is occurring here, right? I'm saying, okay, this is the thing that's member of you, and this is what to put in the sum that I return. Do you see that? This is the particular concrete value to put in, right? Okay, now what if I were to do this? What if I were to do this? A most unpleasant thing. Okay, suppose I were to say this. Do you think this will be fine? Yeah, fine. What if I were to do this? Do you see where I'm going? Yeah. Well, what will happen? Do you think good things will happen? Will this be a thing of delight? Okay. No, so something bad happened. Something unfortunate happened. Or to use an example that maybe it's going to be more even clear about this, I'm going to make something bad happen. And then you're going to tell me how to work around it, okay? We're just going to rehearse this understanding. This is map. We tell each element, that comes in, we tell what to put in the resulting collection. You understanding this notion? Okay, now watch this. So suppose I were to do, okay, we're going to be back to this. And suppose I want to do 10 divided by x. Is this going to be okay? That could be okay? Okay, now watch this. Suspense grows. What's going to happen next? Do good things happen? No. Bad things happen. A bad thing called an arithmetic exception. Right? Okay, this is not a good thing. So what can I do in Scala to prevent this? Okay. Yeah. Wrap this in a try, right? Make sure before you do this that you imported try by scala.util up here, right? Yeah. So we have our try. Okay. So we'll give this a college try. Here we go, right? Boom. Okay. Okay, did bad things happen? Well, sort of, but they were contained, right? This is, after all, a value. This is not a value. This broke out of the value, said, like, I don't know what to do, and it ran off screaming, so to speak. It was not a happy camper. This did not return a value. It returned an exception. Did this return a value? It most certainly did. This is the value it returned. But it had a try there, right? And similarly, if I had had this originally be, try of this, it would have returned a try. Okay, so ladies and gentlemen, now if I had try of this, what is this going to return? Do you see a problem here? What is this thing that this returns? Or conversely, we'll stick with this. So if I do try of 0, suppose I have a computation that happens to return 0, and then I undertake this. What am I getting out?
A try of try.
Getting a try of try. It's a success of a failure. Is that what I want? No. What do I want instead? What operation instead of map do I use when the thing that I'm computing can itself cause an error, or it needs to return a monad? You use what? Flat map, ladies and gentlemen. Flat map. And you may have, you can be excused if you originally thought that this is a sort of hack. It just kind of combines it down. But it turns out flat map is absolutely central in monadic operations. And this flat map allows us to take an operation to operate on a monad, but with an operation that itself returns a monad. It doesn't just, remember up here, we were returning values to substitute in for this concrete value. Remember, so if we had a, sum of 3, this would tell us how to go from a 3 to a double, right? Now we're no longer having that. We're having something that goes from the equivalent of 3 to, concrete values to a monad, right? To a monad. And the job of flat map is to mesh that monad with whatever monad it's calling on. It's being called, upon which it's being called, the monad that is used to invoke this. Does that make sense? And this guy here, the guy that I've selected, is precisely this one here. It's just, we call flat map on this guy, passing it this as an argument. And note that, do you see the type of this? Is this type B? No, it's type monad of B. This is a monad. Wherein lies that monad in our example? There it is in all its glory. Do you see that? Do you see that? Okay. So this is this monad of B. And what does this whole thing return? It returns a monad. And just to correspond to that, what does this return? It returns a monad. Do you see that? So this is more subtle than map. Map just told us how to replace each element by another concrete element. And it really didn't have a monad as part of this, right? Or if it did, it got nested in. Remember we tried this map and the monad got nested into it, right? Here, flat map, we have a monad. We invoke flat map on it to return with a function that returns a monad. And this has to turn them into a single monad, right? It has to sequence them. It has to combine them. Now, how it combines them, and this is a very important point, how it combines this monad with this monad depends on the monad involved. Okay, why do I say that? Well, for a trimonad, what do you think is going to happen? Well, will this guy even, this function right here, for this particular case I'm looking at, is this function even going to be invoked? No, because this is already a failure. Okay, and yet if we had this, it would be invoked, right? It would be invoked. If we had this, it would be invoked. So what flat map does to combine the monad that's on which it's called with the monad returned by this function will depend on the context. Similarly, if we had option of 3, oops, mumble. Yes, indeed. So it's looking for. So forgive me if I do this, because it's actually looking for something of the same type in this case, which is unfortunate. Scala's constraint here, but here it's giving it an option, and this is a monad, this is a monad, and it's returning here the monad that results from this because it knows this is a concrete value. By contrast, if I did none here, I computed it earlier, right? 02. If I did none, it will give me back none. This is not even invoked. So for each type, option, try, stream, vector, etc., it knows what flat map should do to be meaningfully sequencing or meaningfully combined the monad which it's called and the monad that's returned, right? If indeed it even calls this. Do you see that? And similarly, for the case you were dealing with, there was a function that knew how to combine random number generators, etc. Okay, so a key point here that I'm trying to illustrate is that the function that in contrast to map, which takes a monad, here we're invoking it on the monad, vector 1, 2, 3 dot flat map. This is the vector of 1, 2, 3. It's the monad on which we invoke it. That would, for map, it would take a function that tells, okay, I take it in to return a double. Do you see that? And then it's going to return a vector of doubles, for example. We saw that earlier, right? That's for map. By contrast, flat map is going to take in a function that takes the concrete thing, here, int, and returns a monad, here, something like try event or option event. Do you see that? So this is flat map signature, and it returns back a single monad that in some sense combines these two. For example, if this one were option, it's just, or were none, it's just returning none. Otherwise, it's actually applying this function to that, okay? So the key thing is this is a function that takes an A, takes the elements of the monad under which it's invoked, and it returns a monad of B, okay? And this monad that results is ready to be given for the next bind operation, okay? Okay, now, this is good. Let's just look at these to further our concrete understanding. For a stream, for example, this represents a possibly empty stream of values, okay, of type T. We've seen this. To handle the case where the stream of T is empty, option, okay. So the two things here for unit, here is stream, right? We take a bunch of values and we turn them into a monad. Do you see that? Take these values, turn them into a monad, and then bind here is flat map. And the function, for example, could take in something and return a stream, right? A stream of something. This says A. It's not necessarily A. We'll do that. So let's go illustrate that. Here we go. Ready? Stream of 1, 2, 3, and we'll give it flat map. That's our bind. That's this function here, right? You see that? And here we're going to go. We're going to give it a function that is going to return, let's say, a stream. Okay? Maybe we're going to do a stream of x and square root of x. Okay? And here, I'm going to be a little bit more pedantic by just making it clear that this is a double. So I'm going to multiply it by 1.0. Okay, actually, we can just, I think you can call 2 double. 2 double here. And I think it will be a happy camper. Okay, so ladies and gentlemen, here we get back a, okay, this is, yes, of course. So what's going on here? Okay. Okay, whence did this 1.0 come from? Good. What will the next element be? 1.0 from where? Square root of that. What will the next one be? 2.0. Yeah, yeah. Okay. So we'll just say force. There we are, right? Here's the 1.0, 1.0. Those are from these guys here. And the next one is 2, and then the square root of 2, and then 3, and then the square root of 3. Do you see that? So here we had bind. It takes a function, which takes in an integer, and it returns a monad, a stream of doubles in this case. And the whole thing returns a stream of double, right? Does that make sense? Yeah. Okay, this should say option, not optional. And oh gosh, this is I don't know. Well, it actually is key for this as well. That's true, because it's true for sort of collection functionality. Got that. Okay. So here we can handle various values or cases when things are absent. And you know, here we have sum, and we have flat map, and the function is mapping in this way, right? Now I said actually this is A to that, but it's actually, truth is it's B goes to option of B. Okay. Okay. Now, okay, this is from Java, but the equivalent is future, and it turns out that we'll probably cover this in a later lecture, but fundamentally we have ways of creating promises and then composing promises. So if I have a promise that goes from, that knows how to, for example, get strings from a website, and then I have another promise that, given a string, knows how to look it up through a web service and get back a value. I can compose two promises to get a complete promise that will take us all the way. Let's talk about another example, though, that isn't built into Java. Maybe we want to do logging. Okay. We want to log operations undertaken in code. So here, the monadic type will represent values being manipulated, but it's going to do more than just perform operations. It might additionally log information or accumulate log information as part of it. And here we can turn a value into sort of a logging value, and bind here, associated with flat map, would take in the original value and a function that performs an action on a value, say, well, not logging that, and it returns a monadic value that is ready for the next operation that's accumulated this logging information. So here, the logging this logging monad might be accumulating the various log messages along the way, in addition to the value that it carries. And it's printing out all the operations being performed on this value as part of the context. And here, an operation is being performed and on a value. And then the results of that get combined with the already logged messages to yield a sort of cumulative log to this point. Okay. Random number generation was something you saw from the book. We may go into that more next time to help unpack any of the notions if there's questions here. But fundamentally here, we're carrying around not just the values, but what in addition to the values are we carrying around? We're carrying around a random number generator, a random number seed, I think, is exactly, or sort of a state of the random number generator. Do you remember that? Mm-hmm. So we have to not just keep track of the value, but we have to keep track of the current state of the random number generator so we can generate more numbers, right? Otherwise, if we didn't keep track, we'd start at the same seed again and keep on getting, say, the same value out. But this allows us to keep track of state, in this case, state of a random number generator, right? Here, it's more subtle. The book's example I find very beautiful, but also very challenging to wrap your head around. That's why my book is marked up in red for this chapter so heavily, where I'm sort of highlighting different features of it. But here, the monad is actually a function. It's actually a function. And in taking a value and bringing it in with unit or pure or return or whatever you're going to call it, it's to return a monad that's in fact a function. And that function knows how to take a random number generator, return a value in a random number generator. Okay, so this says random number generator paired with a value. Okay, we may go into that some more. Another example that I might note would be for a monad, you might have a monad that keeps track of coordinates of a point. But associated with that information might be metadata in the form of what coordinate system are these represented in. Okay, so you might have 3 coordinates, X, Y, and Z, but there's a coordinate system in which those are represented. You know, maybe you've done rotations of it or rescaling of it, and you want to keep track not just what is the coordinate of this, but what is the coordinate as expressed in a particular coordinate system. And here you might have operations that perform calculations on it, and that yields a new characterization of the coordinate system. And you want to keep track of, therefore, not just the vector, but the vector and the coordinate system that gave rise to it. Okay. I won't go into this right now, but it's an intriguing example, and it's really useful when you have multiple coordinate systems being used in your scientific code to be able to have clear provenance, like, and to be able to translate between them as needed. Okay. Another case would be we're accumulating values and where those values were computed within the program, or where, on what data sources those values were computed. Okay. Now, I won't have time to go into it today, but it's a topic we'll return to a little bit next time. You may be wondering, given my description here, why the example in the book uses functions, but the examples we've been talking about here don't seem to be using functions for monads. They seem to be much more familiar quantities like sum, you know, like an option, which records, is this empty or not? Or maybe a value which knows, did this cause an error or not? Or maybe it's, you know, a collection of values like a vector, right? If that's a monad, you may be wondering, why in the book do we have this monad that's represented as a function? It's a function of state, okay? The monad itself is a function. And I'm going to try to address that next time by talking about 2 types of monads. And a key differentiator is sort of how much the function that's passed in as an argument, how much information does it need outside of a particular concrete value? To what degree does it need information about the monad on which it's being invoked? Okay, so let's go back to our example here. You know, one of these examples. This guy here, this function, to operate, this function, to operate, does it need to know, at the time that you invoke it, does it need to know all about this monad? Well, a key thing here is this function, when is it invoked? Is this function invoked in this case? Is this function run in this case? It most certainly is. It most certainly is. Is this function invoked in this case? Well, okay, let me do it with try. Is this function invoked in this case? I would say it actually is. It just happens to return a failure. To sort of make it clear, is this function invoked here? Yes, it certainly is. Let me ask this: if this function, if I do try of 1 divided by 0, is this function invoked? No, it's not. It never actually gets invoked. Yes. So it actually, this function itself, Whale is exactly correct that whether or not this function gets invoked here depends on the value of this monad. But if this function runs, it doesn't need to know about this. Okay. Similarly with that option thing earlier, if I had, do you remember I earlier defined an O2? Oops, O2. Do you remember that? It happened to be none. So let me ask this: if I did this, is this function ever invoked? No, this function is never actually run. So this function by itself doesn't need to know about this. Okay. By contrast, there are cases where, in order for this to do its work, it needs to know about the metadata. An example is random number generation, where for this function to do its work, to generate a new random number, it actually does need to know about the state, the random number generator seed as maintained in this, okay? And there we have more sophisticated needs that I call kind of state detail sensitive monads. These are ones that care about this state or information metadata being maintained. Whereas then there are some that are not. They don't care about what's in the package. They just get invoked or not based on that, okay? And we'll talk about those couple types. But fundamentally, monads are a very powerful way of allowing us to achieve these goals: transparency, concision, modifiability, modularity, and the pipelines, allowing us to deal with exceptions, handling special cases, asynchronous operations. But more than that, they allow us to keep track of extra information. They allow us, and this goes to this notion of programmable semicolons. They allow us to keep track when we're keeping track of values. They allow us to keep track of a whole lot of other things, where what we keep track of is monad specific: logging information, transformed coordinates, provenance of a value, where in the program the value is computed, whether the value, what units the value are in, whether it's empty or not, whether in fact we have a value, where it needs to be computed, whether it's computed or not, how to compute the next value. These are examples of information that can be maintained by monads. And by keeping that information together with the value as a value, these are monadic values, we can then use pipelines to do our computations. And all that information is threaded through automatically. It's just threaded through the entire computation. Not just the core values themselves, but all the metadata about them, all the extra information, the logging messages that we want to perform, etc. That's all sort of accumulated along with the values. And this affords us a way of taking a given pipeline, and layering into that existing pipeline rich additional information we want to carry around with those values. So we could have that same pipeline now computing, doing computations about logging, doing computations that allow us to trace what's going on, doing computations that are robust to error handling, etc. Okay, So this is the promise of monads. We'll go into it a little bit more detailed next time, okay? But it's one of the reasons that they're so recommended in data science for Spark, because we do want to keep track of provenance. What do we have to keep track of in Spark? Does anyone remember my comments and maybe the opening lecture, the second lecture? Why do we want to keep track of provenance? Why do we need to keep track of how a value was created? Say a data set. You can recover it from it. So that's a great example. Another reason is if memory is short, because it's a functional set of computations, if memory is run short and we don't have the luxury of storing this value anymore, what can we do? If we know how it was computed, what could we do? Yeah, we could throw away the actual big data set, the big honking data set that's taking tons of memory, with the confidence that we can recompute it later, because we know its lineage. We know where it came from. We know how it got here. And so if this data set is too big to store in memory now, toss it out. We can recompute it later. We can recompute it when we have the memory to spare or when we need it, right? And it turns out that in as much as monads support streams, for example, this ability for them to be computed, we can also do incremental computation, this kind of memory sipping computation where we only do the work at the time we need it. And therefore, we can process each element along the entire pipeline rather than having the pipeline have to recreate giant data structures for each step of it. We could perform that computation incrementally, which is also of great value. So monads are really useful there. They're really useful in general, though, for flexible software engineering. And it's one of the reasons we're looking to make them, for those interested, a central point of our language for agent-based modeling, FRAPGIS, which some of you might know Alex was working on last summer, and which is going to be an important part of our research program in coming years. Anyway, that's all for today. I apologize for the bad air quality. This it's quite horrendous. I came close to asking Christine to sort of ask FMD to come over and investigate, but hopefully it'll be better next time. Okay, thank you very much. And I have a couple of minutes where I could talk to people, but because of last week's unexpected events, I'm going to need to take the time between classes, my next class being at 1, to meet also with another student with Ivan. But I'm glad to talk for a few minutes. Okay? Thank you very much, ladies and gentlemen. Next time, we'll explore more with monads. Thank you.